Okay, our next section focuses on something called trig substitution. So trig sub can be used to evaluate integrals of a certain type. And they will be ones that involve usually some radicals or rational exponents, such as square root of a squared minus x squared, square root of a squared plus x squared, and the third type is square root of x squared minus a squared. Okay, so now I put radicals over these, but it could be, to the 2/3 power or to the -1/2 power or so on. The main goal of doing trig sub is to eliminate the radical. So the first one we're going to do is for integrals involving square root of a squared minus x squared. We're going to let x equals to a sine theta. And the domain restriction here, which generally you guys aren't going to have to worry about, is going to be theta between -pi/2 and pi/2. If you see the a squared minus x squared, you want to use x equals to a sine theta. So our first example, we have dx over x squared square root of 4 minus x squared. So if you notice, I have a radical with something squared minus an x squared. So this is going to tell me that x should equal to a sine theta. So do you think that should be 4 sine theta or should that be 2 sine theta? Well, notice it's a squared minus x squared, so 4 squared is our a squared. So this should be x equals to 2 sine theta. So dx will equal to 2 cosine theta d theta. So we are going to substitute in 2 cosine theta d theta into our numerator. We have an x squared on the bottom, so that's going to become 4 sine squared theta. And then we have our radical, 4 minus 4 sine squared theta. So let's take a look at this part, the 4 minus 4 sine squared theta. I'm going to rewrite our numerator. I'm going to rewrite the 4 sine squared theta in the front. And I'm going to factor out the 4. So I have 4 times 1 minus sine squared theta. Now, what do you guys know about 1 minus sine squared theta? What is that equal to? That is a cosine squared theta. So I'm going to take my time and write out all the steps here. This is going to be a 4 cosine squared theta. And you should notice that the square root of 4 cosine squared theta is going to be 2 cosine theta, which is going to completely cancel out. So now all we have left is really a 1/4 sine squared on the bottom, which is a cosecant squared theta. And do you guys know how to integrate a cosecant squared theta? That's going to be what? Negative cotangent theta plus c. Okay, so it really worked out nicely. We use the trig substitution because we can use the Pythagorean identities to simplify stuff. One little catch here at the very end, we have to put our answer in terms of x. Do you notice our original problem was in terms of x? We need to have our answer in terms of x. And the way that we do that is really quite fun. We're going to take this original problem that we had, or the original substitution that we had. I'm going to write this out as x over 2 equals 2 sine theta. And we are going to draw a triangle. We are going to draw a triangle with an angle theta, and the sine value is x over 2. So using the Pythagorean identity, I can fill out my missing side, and then I will back substitute. So I have negative 1/4, and cotangent theta in this case is going to be adjacent over opposite, so square root of 4 minus x squared all over x plus c. And this is our answer. And I'm going to try the second type of problem that we have. I'm now going to cover the second type of problem that we have for integrals containing the square root of x squared plus a squared. We're going to let x equals to a tan theta. And the restriction on our domain here is theta must be between pi/2 and -pi/2. And let's do an example for this. The integral of dx over square root of x squared plus 9. That I have x squared plus a squared down here in the bottom. It's an x squared plus 9. So I'm going to choose to let x equals to 3 tangent theta. So dx will be 3 secant squared theta d theta. Again, be really conscious about writing your dx's and writing your d thetas. So dx is 3 secant squared theta d theta in my numerator, and in the denominator I have 9 tangent squared theta plus 9. Remember, this is all about the Pythagorean identities. So I'm going to factor out a 9, which leaves myself with tangent squared theta plus 1. And what is tangent squared theta? Tangent squared theta is secant squared theta. Now this is still under the square root, so make sure you're careful when you simplify this. One of the most common mistakes here is people actually forget to take the square root and they cancel out all of the secants. Really, this is 3 secant theta on the bottom, so we're left with a secant theta d theta. Okay, now, do you guys remember how to integrate a secant theta d theta? This was on one of your previous homework problems where they gave you a hint. And I told you the next time you see this, it'll be in another problem, and look, it's actually part of this problem, and you don't have a hint for it. Okay, so what you have to do when you have a secant theta is to multiply top and bottom by secant plus tangent, so that we let u equal to your denominator, which is secant theta plus tangent theta, and the numerator, secant squared theta plus secant tangent, is actually your du. So if you want to do a u sub here, you can, or if you don't want to, that's also okay, if you know how to do it without it. I'll go ahead and write it out. This leaves us with a 1 over u du, which is a natural log of u plus c, but we can already back substitute right away. It's going to be ln of the absolute value of secant theta plus tangent theta plus our constant. Our original substitution was x equals to 3 tan theta, so x over 3 equals to tan theta. So using the Pythagorean theorem, x squared plus 9 for our hypotenuse. And we can say that our final answer is going to be natural log of secant, oops, can't see my triangle, secant, which is going to be square root of x squared plus 9 over 3 plus tangent, which is x over 3 plus c. Now I just want to do something a little different here and share with you guys how we can rewrite this. We can combine these two to be x plus square root of x squared plus 9 all over 3. And then I can actually separate this natural log using my properties of logs and make this minus ln of 3, which is simply a constant. So this is actually ln of x plus square root of x squared plus 9 minus or plus some new constant. Now why am I pointing that out? Again, because half of your AP test is multiple choice, and what if you saw this as your final answer, but you wrote this up here? You would need to know that they are actually the same thing and not choose, for example, a none of these as your answer. You wouldn't want to get that wrong just because you didn't know how to recognize the right answer. Okay, for our third and last type, it's going to be integrals involving the square root of x squared minus a squared. And in this case, we are going to let x equals to a secant theta. And our domain here, theta is between 0 and pi over 2, or between pi and 3 pi over 2. So again, you really don't have to work too much to remember these restrictions. That's just the restriction on the domain. Third example, integral square root of x squared minus 25 all over x. We're going to let x equals to 5 secant theta, so dx will be 5 secant theta tan theta d theta. Plugging everything in, what do we have? Square root of 25 secant squared theta minus 25 all over 5 secant theta. And see, if you're sloppy and don't write the dx up here or down here, you're going to miss this whole last part, which is 5 secant theta tan theta d theta. It is a big thing to miss. We can cross out the 5 secant theta. We can factor out a 25 and have ourselves a secant squared theta minus 1. times our extra tangent theta d theta. Now what is secant squared theta minus 1? That's going to equal tangent squared theta. So we have a tangent squared theta. Make sure you still remember that this is underneath the square root symbol. So when we take it out from under there, we have 5 tangent theta times another tangent theta. We now have 5 tangent squared theta. Not a cubed, but a squared. We had one of these on our homeworks the other day. How do you integrate a tangent squared? You need to substitute. What are we going to substitute it with? Again, Pythagorean identities. Secant squared theta minus 1, which gives us 5 tangent theta minus theta plus c. Now, is this our final answer? Nope, not quite. Remember, we have to back substitute. That means to draw a triangle in order to back substitute. Our original substitution was x equals to 5 secant theta, so that means x over 5 equals secant theta. So hypotenuse over adjacent, and our missing side is x squared minus 25. So when we back substitute, tangent theta is opposite over adjacent, and I'm going to write this out as square root of x squared minus 25 over 5 minus 5 theta. Now how do we write theta? I'm going to go ahead and just use arc secant because I'm given a secant. So I'm going to say arc secant of x minus 5. Can I cancel out this 5 and the 5 inside my arc secant? Be careful, you cannot, because this is a ratio inside our function arc secant, so do not cancel that out. Now I know some of you guys may be thinking, oh my gosh, how am I going to remember which to substitute with? Well, you can try to remember that there's just sine, tangent, or secant. And if you work out all your math correctly, and you, for instance, happen to choose the wrong one, because you can't remember which one, it won't work out. Okay, so for like this particular problem, which is dx over x squared, radical 4 minus x squared, which was our first example, it uses a sine as a substitution. Now let's say you forgot and you got confused and you didn't know which one to do. And you thought, oh, maybe it's the tangent. So you let x equals to 2 tangent theta. Let's take a look and see what would happen just to this part of it, because this is the important part that we need to simplify. This radical would become 4 minus 4 tangent squared theta. So we factor out the 4, and we have 1 minus tangent squared theta. Well, we don't have a Pythagorean identity involving a 1 minus tangent squared theta, because our identities are tangent squared plus 1 equals to secant squared. So this isn't even possible. You're going to get stuck at a point where you can't continue. So now what if you thought maybe it was secant theta? So x equals 2 secant theta. So we plug that in. We're going to have 4 minus 4 secant squared theta. We'll factor out the 4, which is 1 minus secant squared theta, which kind of looks good, because I know 1 minus secant squared theta works. I can move that over, but it's going to equal a negative tangent squared. Now I have negative 4 tangent squared theta in the bottom. We're not going to have irrational numbers here, so that doesn't work either. Okay, so the lesson to learn from what I just did right here is that if you can just remember that your substitutions for trig substitution either have to be sine, tangent, or secant, if you happen to choose the wrong one and you remember your identities properly, you'll notice when you choose the wrong one because you're going to have a radical that doesn't simplify properly. Okay? And that's it for today.